Okay. Uh, Hello, everyone. My name is Hunter Frey. I'm the team leader here for the Regolith Removers at University of Florida, and the rest of the team is I am Cole Plata.
Kyle Lackey for Broski.
Andy Rodriguez.
Yeah. And today we're going to take you through a presentation talking about a design challenge set for a lunar mission. So first things first, the lunar mission itself. I double skipped. There we go. Okay. The mission itself is involving the Artemis mission, which is America and humankind's return to the moon. It's the 80s in the Apollo program. The Artemis mission seeks to establish a long-term presence on the moon through the use of the Gateway space station, lunar bases, and lunar exploration and refueling stations to fuel later Mars missions, asteroid mining, and just how to live on another planet. However, there is one major roadblock, not necessarily preventing, but hindering this Artemis launch, and that is lunar regolith. This is where the Human Lander Challenge comes in. This is a program sponsored by NASA, and it's an international call for help, asking for students and teams from both undergraduate and graduate levels to submit ideas on how to deal with the lunar regolith problem itself, either plume surface interactions and all kinds of different factors that go along with it. The project requirements, as you can see on screen, are pretty varied in what you would expect to see on something designed for a lunar mission. The most important ones that we felt that and what drove our design was cost effective and 3 to 5 year launch timeline, along with no risk to the crew. And we think we accomplished this pretty well. The reason for it was because we don't want to hinder these programs or this launch vehicle.
Yes, so we were looking at the different PSI for plume to surface interaction issues that can happen during the lunar mission. So this includes vision obscurity, which can cause the astronauts to have a difficult time landing. And an example, this was on Apollo 14 as they landed on the edge of a crater and the lander was tilted. You also have different health hazards and health risks because the astronauts can breathe in the regolith and that can cause respiratory issues. You also have the mechanical parts or mechanical components on the landers getting clogged by regolith buildup. And you also can get false readings on the different instruments. We also, despite this, we wanted to make sure that our primary target was visual obscurity because we believe that this issue should not be understated and that there's current gaps in the technologies right now to solve this issue. So we were looking at the different solutions right now, and one of them is electrodynamic dust shields. So this uses two electrodes and an alternating current to create a dynamic electric field to repel different charged particles. And you can see here, there's an example on the ISS. You have a before and after picture. There's also electrostatic lunar dust collectors. This uses charged plates to attract the particles and collect them. Example right here. And you also have electron guns, which use a beam of electrons to repel the charged particles away over time. And there's nylon brushes as well that have been used on Apollo 14, for example, on the thermal degradation sample test. So there are caveats to these solutions right now. For the electrode solutions, they only work on ferrous materials, and these technologies are very complicated because there's different problems with them right now. For electrodynamic dust shields, they use a very high voltage, so they can cause a huge health risk for astronauts on board. And for the dust collectors, they also can damage instruments and can also give false readings as well. And then for the electron guns, they can damage the structures. These also use a lot of power and can put a lot of weight on the lander itself, which leads to our current solution.
Across all these types of different solutions, when we were coming up with our design, we wanted to design with a very simple concept in mind. And this would have led to all kinds of weird solutions. And we wanted it also to be flexible in adaptation. We chose to use the Starship lander as our test subject for this, but this technology we found we wanted to be flexible for other landers and other systems on the lunar surface. We found through our research piezoelectric plates, or PZT plates as we'll refer to them as, and these little electric plates ended up being the core of this entire design and allowed us to accomplish our two design goals.
So piezoelectric materials
how they work is, so it'll have a voltage going through it and the material will expand and contract. And that happens at a rapid rate, which produces the mechanical energy that leads to vibration. Current technologies that use this are really the ultrasonic cleaning industry. And if you know anything about that, that uses cavitation bubbles that are produced when it vibrates in water. Those bubbles burst and it cleans the material, as you can see in the video here. It has not yet been used in any way that we've found for what we're trying to purpose it for. It's relatively new, so there may be some kinks that we're not aware of, but it does have a lot of promise. So this idea really stemmed from this article. In the article itself, it showed that you can use PZT plates and apply them using epoxy to a material and apply a current through that material, and it will vibrate it or through the PZT, and a PZT will vibrate, causing the material to vibrate, which any dust on the material, as you can see here, will come off. So if you apply that to Starship, if we apply to the windows of the visual systems, so the camera's looking out the window's covered in dust, you have a PZT plate on like the corner edges, on each corner edge, the voltage is applied through it, it vibrates, it causes the window itself to vibrate, and the dust that is on it will come off, in theory. As I said before, cavitation is the current use of this technology, but we're going to use the conduction and the vibration that is caused by it for our design. So I know this does look simple, but in essence, it is a simple design. All it really does have is the PZT plates on the corner edges, the component box, which will have the power distribution board and the voltage regulator to get the voltage through to the PZT. And there will be wires stemming there to these that will be soldered on. The component box itself, as it will be on Starship, will suffer some radiation, so there'll be multi-layered insulation that's commonly found on Starcraft to prevent any of that radiation from leaking through and causing damage to the components. The actual component box itself will be mounted onto the ship using bolts.
And it's internal instead of an external mounting. So it's keeping inside to keep it to minimize flight dynamic problems.
So as I said before, it's a pretty minimal system, so it's meant to be minimally invasive. It's supposed to integrate with the existing systems. It will be connected to the power systems. It will be a relatively minimal amount of power that'll sap from those systems. It won't obscure the vision of the cameras as it'll be on the corners, and it should help with any dust that collects that is not gotten rid of through the existing systems.
All right, so for our structural analysis, we analyzed the place most likely to fail, which is the thin PZT plates. And PZTs, when operated under the inverse piezoelectric effect, to get that oscillation, is very unlikely to fail due to cyclical fatigue, as PZT actuators, for example, on a lot of the satellites can undergo billions of cycles before failure. So the main way these things are going to fail is through your applied voltage, which needs to be below a certain level that it's not going to exceed the dielectric strength of the material, which is when it will lose all of its piezoelectric effects. And this can be estimated by using the coercive field strength to multiplied by a certain factor, which will give you your breakdown field strength, which can't be exceeded. And with an operating voltage of 100 to 200 volts for our design, we have a factor of safety anywhere from 2.5 to 5, which allows it to be implemented pretty easily into the Starship. Now for the thermal and electrical analysis, the PZT can operate in pretty harsh environments, from ranging in a recommended range of negative 40 degrees Celsius to 150 degrees Celsius, which can be even improved if you change your composition of your PZT and if you use different epoxy. And the number one thing you got to worry about for degradation is humidity levels, which if they exceed 75% is going to start degrading your PZT. The humidity levels aboard the lander are about 60%, so that shouldn't be an issue. And outgassing is something that can happen to non-metallic materials when exposed to harsh environments such as vacuum or high heat. And this is the process by which the material will release gas, which will basically cause it to expand and fail. And this can be prevented using very common aerospace grade epoxy, which is low outgassing. And the heat load for our design is actually very minimal, which with each plate only drawing about a watt each, so a total of 4 watts for the design. And this leads, if we have an operational time of about 30 minutes on average, it's only about 6 to 7 BTU per operation, which is easily handled by the heat sink aboard the ship. So when it comes to growing inflation and the increasing entry level cost-wise for the space industry, it is imperative that a beneficial solution is low in cost, which is why our solution aims to be roughly $1,400 or $1,040 per implementation, which if you look at the total cost of the Starship lander, that equates to roughly 0.0004% of that total cost. So when it comes to space exploration, weight is arguably one of the most crucial factors, because if a solution is heavy in weight, that takes away from the payload you can bring, the crew, and the machinery. Therefore, our solution will equate to roughly 52 pounds per implementation, which is, if you look at the total fueled mass of Starship, is roughly 0.0004% of that total mass. When you are in space, there are certain amounts of both power and resources that you have available, which is why our solution aims to be as low power consumption as possible, only equating to 4 total watts of power consumption, which is much less than some current solutions on the market, such as Sparkle, EDS, and ELDC. And its effectiveness, there have been countless studies showing its effectiveness, such as a 2022 study by the Research Center for Humanoid Solutions, which concluded in quotations, PZT could be one of the most promising methods of dust removal. So due to its rather simple design, small size, we estimate that it'll take about roughly a year for development, followed by a period of 6 months for testing and evaluation, and should be ready for implementation into Starship's current systems and ready for the moon in roughly 3 to 5 years. So not only can this solution be applied to sensors and cameras, it can also be applied to many other materials on the landers, pretty much all material on the landers that you can fasten it to, such as the external parts of the ship, landing systems, you name it. It is very versatile. And it can also be applied to mission critical systems that are off the lander, such as spacesuits, landing mechanisms, and countless other mission critical systems, making this solution not only viable for this implementation, but hopefully for many future implementations when it comes to space exploration. Thank you.
That's our
Thank you.
presentation.
So how many minutes in total? What time did you guys start?
I don't know. It's probably estimated around 15 is what we were getting, 15 to 20. in that
I
range.
started at 10:49. Okay, here you guys, 30 minutes presentation.
Well, sub 30 minutes.
What?
Sub 30 minutes, not 30 minutes.
Okay.
Alright, so you guys have 50 pounds of something, but I am not at all clear on what that something looks like, right? So you gave a very high level, almost marketing style presentation, but I didn't get a sense of any of the engineering, right? What does it look like? How does it integrate with things? How, you know, when you put something on a window and shake it, you know, what is natural frequency of the window compared to the frequency that you're actuating it at? How does, how does dust removal, you know, go with, frequency with amplitude? Like I didn't get any of that. So do that. Do you have any, like, can you talk to any of that?
Yes, so the study that I saw uses 30 kilohertz to 80 kilohertz, so anywhere in that range it can oscillate and remove dust. There is a maximum efficiency range, but that varies per material, and we're not 100% sure on the window material for Starship specifically. The resonance frequency, as long as they make it not, well, the resonance frequency of the window, they have a 50 kilohertz range to work with.
Okay. What do you expect the natural frequency of say a window on Starship to be?
So a lot of that stuff for the natural frequencies is verified experimentally, which we weren't able obviously to make a full prototype. But the glass on the Starship uses Rycore tempered glass. We actually weren't able to find like an exact natural frequency range through our research.
Well, you're not gonna find a natural frequency range. You're gonna find a stiffness and you're gonna find a size, right?
Yeah, but we don't know like for the Starship, we don't know the exact. All that's like proprietary. We don't know the exact sizes of anything, exactly where it's like what this.
Ballpark, can you say, all right, well, I can see a picture of it and it's about this big. Like I know Starship is 6,000 feet tall, and I know the window is like this big, right? So it's 14-inch, square panel, right? And if it's got to withstand 1 atmospheric pressure with a 1.5 safety factor, it's probably this thick, right? And so now we're going to talk about natural frequency of that compared to what you would be able to actually like. I need something, right?
Yeah. We try to base a lot of our research on the Apollo data that was readily available. So it was hard to we failed on that aspect of translating it directly to a Starship application, just because we were running into brick walls in terms of proprietary information about like exactly what they were doing and how they were using it. Plus, the camera lenses we don't know, or the camera windows we don't necessarily understand, like know the exact dimensions because we don't know exactly where the cameras are for this application and all that. So we try to ballpark it as much as possible, but we were unable to do it fully.
All right, so 50 pounds. What comprises those 50 pounds?
Subject to change with the design as we're still evolving it. Mainly when we were doing the power stuff, we realized we needed to add the insulation. So we wanted to give a very high-end estimate, and then we could adjust the size as needed. Because originally it's comprised of aluminum. The PCT plates themselves are super light. The component box itself, it's a black hole in terms of exactly what we need and how we need it, because the voltage regulator or the power amplifier might be a different size than what we can find readily available. It might need to be custom built for this, and we weren't going to do all the electronic work for it. So we should have that's why we're estimating 50 pounds max per implementation. It's probably going to end up being a lot less, considering it's mostly just an aluminum box with all the components inside. But we just don't know what the weight of the installation, the individual power components, all the wiring, all that. We were unsure how to necessarily get to that.
Okay. The other approaches that you kind of talked about at the beginning of the presentation, ballpark those in terms of how they compare to 50 pounds.
We're not necessarily sure, but the electron guns are pretty hefty in terms of like an actual industrial scale use. The ones that they use in the lab are full solid metal, and they're relatively large to even produce the electron beams. So to apply that to a ship that can shoot out an entire laser grid of that to charge the ground before the Starship even lands, that's pretty size-wise, pretty hefty compared. And then we were also comparing with other solutions, both in this class and that we've seen, where they deal with more abrasive materials, where we saw solutions upwards into the ton range, multiple tons and subpar tons, even like changing out the landing gear was a significant weight. So that's why we were trying to design something that was really designed to be a low-weight solution.
And do you have a estimate of effectiveness? Like what's your requirement for dust removal? Like what are you trying to quantify, quantify what you are trying to achieve?
Well, we're looking for at least 90%, and from the studies we've seen, 90% is a very reasonable goal. Like in the pictures I showed you, that was about 99%, I think they estimated effectiveness of removing dust. Of course, space is going to be a little bit different, but we can imagine it'll be within a 90% range. which shouldn't obscure any.
And we're
vision.
hoping with the way the mission itself works, where it's going to be running before it even lands. Like if dust becomes an issue, it's going to be just constantly reflecting the dust. We're hoping for higher effectiveness. This system is also designed to be a backup to the EDS and those types of systems, where they'll work together to both block ferrous and non-ferrous materials. So
Okay, so
doubling
you're not
effectiveness.
replacing those tons of weight that you say need to be added for other systems. You're supplementing.
Specifically for vision. I don't know necessarily, we weren't necessarily trying to do the structural integrity where like the abrasion from stuff just ramming into it a whole bunch, which is where this multi-ton solutions came in. This is really designed to both be a standalone solution for critical systems and also a solution meant for helping out the EDS, because not everything is going to be ferrous, and the EDS won't reflect anything that's not ferrous. In case the EDS fails, or in case this fails, as backups to each other, improving the safety of the mission and helping out with visibility.
Okay. And the other thing I'll say is when you talk about the 50-pound weight, you said that's 0.004% of the fuel mass of Starship, right? But from a design perspective, I don't care what the fuel mass is, right? I care what the payload mass is, because that 50 pounds is coming out of my payload, right? So that's the comparison to make.
Okay.
Right. So for future spacecraft work, right? And anything you want to add is taking weight out of payload. So that's what you want.
Understood. So the biggest recommendation would be to just focus on figuring out with the showing more comparisons about like the natural frequency and that kind of stuff.
Biggest recommendation is like show me some engineering, right?
Okay.
Like show me something.
Okay.
Yeah, it could be structure, that could be electrical design, that could be literally anything. But like this was a good marketing presentation, but it wasn't an engineering presentation.
Okay. Understood.
Yeah, I feel like you definitely should take full advantage of this 30 minutes. I mean, I don't want students like exceeding 10 minutes, 20 minutes. Like I ask for 30 minutes and then you talk about like 50 minutes. That's something because it causes stress to the audience. But when I say 30 minutes, I want you to take full advantage to show more content to us.
Okay.
Of the 30. You finish everything within 20 minutes. I feel like I want to see more. And also for the whole semester, including the report every week and everything, I think I already talked about several times that your design can be simple, but your analysis, you are showing your capability as engineer, and everything the work, the research you did behind this simple design should not be simple.
Okay.
Because this, you should have a lot of research and analysis to prove that why your simple design is good. If this is a competition with other group, I showed the report the other group, they have every report, they are so much longer than yours. I'm not saying that a longer report always better, but I don't see much information in your every report. That's what I mean.
To be fair, the proposal that the class is designed off of limits the page count to about 14. And we were
We are
aiming for
not really like that competition is that competition, but this is 5 students work for 3 credit class. UF require every 3 credit class every one of you need to work for 12 hours. So every week's work should be 60 hours work. Do you really feel your report is 60 hours work?
That's why we wanted to talk to you too at the beginning of the semester, like making sure that the design would work for the class instead of the competition. And
Class is
yeah.
class. Class is class.
Yeah, no.
Whatever you said, competition, that's a different thing.
Yeah, no. That was our biggest.
Participation competition is actually not a requirement for, but class is class.
Yeah.
We have requirement for the class. I want to see some actual, you show your capability as senior engineer.
Okay.
Your design can be simple, but the analysis, your capability should not be like, I don't have anything to say. I show you the report of other group. I'm not saying the longer report was better, but I want to see something when I grade the report. I want to read something to see what your level is. Let me go back to the structure analysis. I use this one as example.
There.
You see here, it just feel okay. PCD is unlikely to fail because of fatigue. Apply bottom mass below something. High safety factor. I mean,
we were trying to keep when you were going through the presentation with us, we wanted to keep all the word count relatively low.
You have extra 10 minutes to work on.
Yeah, no, I know.
Show your work.
And that's why we wanted to do as much as like what our first run through and improve on the final presentation.
I want to see something. I think I talked about it, you guys, just before structure analysis part report. I said, okay, you have voltage. what is the, it's not like, okay, higher this voltage, you will fail. All things are voltages, it will not, it will run infinity. It's like, there's a voltage, what is stress caused by this voltage on your structure. And for this stress, how many life cycles of yours based on the structure itself, because your design is simply for your design. So it's not like I have voltage threshold, it's higher than the voltage, I fail. You lower this voltage, I fail. I'm safe. I really want to see some your actual structure analysis, make a connection of the voltage with the force applied on your structure, and based on the structure itself, your geometry structure, material structure, what is stress of each cycle load, and what is life cycle you calculate to prove that it's high safety factor. It's not. I want to see some something.
Like more numbers?
I will say for that, like all those stuff online about piezoelectric material, it defines it based on the applied voltage. Like they don't talk about it based on the stress because its voltage like leads to like whatever your voltage is proportional to your stress basically through a piezoelectric constant. But we didn't really want to bog it all down with all that kind of jargon, like what you were saying in class. That was kind of confusing. So we didn't really want to go like we can add more of that stuff, but it really is like about the voltage is really where the failure comes from. It's all about like the breakdown field, the coercive field strength, and the dielectric strength of the material.
The field strength will cause some force, right?
Yeah, it causes a stress.
What level of stress? What level of force? What level of stress?
Well, yeah, it's based on the applied voltage. So it's the applied voltage, you have a constant that's basically voltage over stress over applied stress.
Make the structure itself much thicker to make it run forever. I can always make the structure thinner and it will just run like 100 times and fail. It's not all about the voltage.
Well,
it also depends on your structure itself.
Well, also for these ones, I think it's also about really like the polarity of the PZT. Once you start surpassing certain voltage levels, the polarity, like you're just going to lose piezoelectric effects pretty much, and the polarity is going to change. So for a fact like that, it is really like not about the stress. It really is about the voltage. But we can, for the next presentation, throw more stuff in about talking about the stress a little more as well.
We found that if the voltage breaks, it's going to break the voltage well before it breaks the material.
How about the thing that you bounded to your to the cover or some sensor? Or
The adhesive?
The bonding.
The
The epoxy?
Yeah.
Yeah.
Yeah, there's aerospace grade epoxy that
Low outgassing epoxy.
So what mean? Because it's okay anyway. So let's imagine he's here to come to hire someone.
Right.
And he want to see your level as senior engineer. You have been trained here for 4 years. But it didn't show much to show your capability. That's what I mean.
We were just trying to sell like our idea or
this is a senior design in aerospace program presentation. Yes, it is like I understand what you mean, but at the same time, this is engineer presentation.
Okay.
You know what I mean? This is engineer presentation.
I just want to say I'm not trying to say anything bad against you. You did say try to make it so you're selling the product. Try
Yes,
not to keep jargon in there.
That you need to convince me. You need to convince me through your engineering analysis.
Rather
You
than
convince me. It just has to be fact. I mean, why? Prove to me. Show me the calculation.
okay.
All right.
So show like
I could tell you the calculation right now. I just didn't think that was like would be understandable. It's
In your report, I didn't see the calculation.
It is in our report. You take
All
the
the
code.
calculation part they are wrong. I told you guys.
That was for the
I'm
The
talking
second
I'm
is
talking
that's completely
for
wrong.
the voltage stuff. Like all the voltage stuff, that's based off.
The voltage part, there was no calculation in your report.
Yes, there was. All right, I could tell you the calculation right now.
Okay. I saw the huge part of static analysis calculation, structure calculation. All of them are wrong.
Yes, for the part that we added as an extra because we thought that there wasn't going to be enough purely with the voltage, and that's what we were trying to talk to you about in class as well. We were asking you like, hey, is this going to work? Because a lot of our PZT failure is involving the voltage, and so we just added the whole diameter.
Yeah, the thing we added was just kind of since it was since it was all with the electricity and whatnot. We just added some structural analysis based off of some estimations of maybe where the bolts or whatever would fail, just because that's not really part of our solution though. So that's why it was probably incorrect. It was just a bunch of estimations, pretty much.
I, I don't have much to say. I mean, there's not much information in your presentation, so I cannot say much. Do you have any other question?
I have something. I don't know what slide it is, but back to there's an example of it working, the before and after pictures.
That's the research slide, right? Previous one.
Yeah.
Yeah,
That one.
so where are these pictures from?
It's from the article. As I was like trying to say, I was trying to say this is what they did in the article and this is what success they had. We weren't able to experiment in firm, but
So from what it seems, and I was talking to you just a little bit before, that it seems like a lot of this is based on this one article, which is the only example of it really working in practice anywhere. I just want to ask, like, what is in that article and what can you actually learn from it and what can you use to actually apply?
a lot of the article was proving that the concept works and then estimating like the range of oscillation, what type of oscillation would make it work best. They were looking for efficiency. They were trying to prove that this concept would work. They showed a lot of like the different oscillations they use, the different frequencies. And essentially at the end, their final takeaway was, this does work and you can apply it to many different materials and it has use outside of this experiment.
The experiment itself was directly applied to like a metal plate as like if it was attached to the outer edge or the outer skin of the spacecraft.
Okay,
So ultrasonic cleansers are already like pretty like a common occurrence. They just haven't been applied to aerospace applications such as this.
So those are
Yeah.
using
Yeah, they use water.
cavitation of fluid, right? So
Yeah.
I mean that's an entirely different mechanism. So I wouldn't
It
say
is.
that's necessarily common.
but this paper is using what you're doing,
Yeah.
right?
Yes.
Okay, so a lot of the analysis and stuff, you can at least use that as a reference, but then you have to make sure that it applies for the system that you're also trying to implement it on, right?
Right. They didn't use a lot of the material science. Most of their focus was on the oscillations. They used different types of oscillation, different ways. That was the focus. The material, they mentioned like brief information about it, but nothing super specific. And they did give ranges for when it would work.
Okay,
Yeah.
so it gives an example of it being effective as a way of dust removing, right?
Yeah.
But they don't do a lot of the actual structural or any of the
They don't.
fatigue or any of that concerns?
No.
So then, have you guys also done that to make sure that you don't have any concerns?
We've looked
there?
into it. Yeah, has a very high limit of like cycle fatigue, plus the maximum amount of usage would be 2. Like 30 minutes is a very high max. It would probably be used for like 10 to 15 minutes on landing, and then on takeoff, it would not even approach a cycle fatigue.
And you're confident that that's the same for any material that it's on?
Yeah, it's based on the PZT itself, not the material that it's connected to.
Okay.
You would adjust the voltage level to hit the oscillation that you want for that material.
Okay.
So if it's like a thicker plate, you need to apply more voltage, and as long as it doesn't break the corrosive field, whatever that field was,
With
the
what?
corrosive field, the electric
yeah.
field, you should be,
Yeah, the dielectric strength.
and that I think the field increases with thickness, right?
Yeah.
Depends on the
And
size of the
voltage.
plates too. The plates are relatively small on this to kind of fit them between layers of tempered glass and to keep their footprint out of vision systems small.
Okay.
But you can make a big plate.
So the thing is you guys can talk about it, but it's just, I think there is a little bit in terms of numbers and what has been done and what has been learned actually in the slides itself.
Okay. All right.
So include more numbers and stuff.
Where would you categorize the technology readiness level of the system?
I forgot how NASA does their categorization, but it's pretty much already there. It's probably, like we were saying, like maybe 1 year of development time because the PZT plates exist. They use PZT actuators and satellites to do micro movements. PZT actuators are also used in toothbrushes, so the concept of an ultrasonic vibration from the plates are relatively known.
Yeah, I mean, I get that. I mean, the basic idea of like running a current through a material and making it vibrate is a thing that people do. But its application to dust removal, I think, is where it is lacking, right?
Yeah.
And so to me, I'm not trying to like redirect the whole project. But to me, it's premature to design a system to, fit on spacecraft. There's still a lot to be learned and demonstrated about, specifically demonstrating the system works with the type of particles and the type of materials at the scale and particularly in a reduced gravity environment, which I know is a difficult thing to simulate here. But I like, to me, before you go design the system to fit on the spacecraft, like that is where the engineering needs to be done. Because one paper demonstrating it is not at a TRL level where you would say, yeah, let's go build this and put it on a spacecraft.
I mean, we had one paper which was a focus, but there are others that we
Yeah.
could potentially reference.
Yeah.
For more, like I believe you mentioned one that you
Yeah,
saw.
what is it?
So, but yeah, I mean, I don't know how feasible it is to like actually build something and find a vacuum chamber that you can sit it in and actuate it with something that is reasonably well agreed, simulates lunar regolith, and
Right.
had the gravity thing is going to be a pain in the ass. I don't know how you solve that problem. But yeah, but I think that sort of thing, demonstrate that it works on a window of reasonable size and thickness, and can you pump enough voltage to get enough amplitude of vibration to actually shake dust off the window like that.
Right.
Like I'd want to see that before, like me as a program manager, say, yeah, okay, let's try this out on which is where your presentation seems like it's aimed at.
Right.
Is like, hey, let's put this on a spacecraft and let's go. So I think that's premature at this point.
Okay. We originally had plans to run an experiment using that paper's design, and we
Yeah.
figured we could do. We were trying to get a video shot of behind the glass and watching it shake it off. We just don't like with all the materials are here in the US. We just don't have the PCT plates, which are a little bit they're expensive and they're hard to get at this
But
level.
you better see.
Hmm?
You better see. After this week, yeah.
Okay.
We won't be able to simulate no gravity, but it
Yeah.
should be enough to prove that it works.
Yeah, I'd like to see that. Just from a buy-in point of view, right? Like before this gets on a spacecraft, like something like that, we have to demonstrate it. And ideally, the test does not just demonstrate it works, but demonstrate that you can characterize how well it works, right? I mean, the goal of a test hopefully is to validate some model, right? And so in that sense, like, hey, maybe gravity is a parameter of your model, and you say, well, if we adjust that parameter, Earth gravity, then we simulate to within 10% the actual effectiveness of the structure. And I mean, if you, I don't know, well, test plane, right? But if you really wanted to go crazy, right, you could say, okay, well, if we're in some centrifugal design where we're increasing gravity and we can still simulate that, that gives us additional confidence that we can go the other way and down to lunar gravity is a sixth of Earth gravity, right? So we have confidence that we can go the other way on our gravity parameter and still be reasonably accurate with the simulation, right? So those are the kind of things to give confidence in the design that a mission manager would want to see, a design chief engineer would want to see before this gets to the stage of, okay, let's figure out how to actually put it on the spacecraft.
Prove the concept before you
Yeah,
deploy it.
yeah, exactly.
Gotcha.
I don't know how much of that is feasible within the scope of class.
Some.
Yeah.
Some of these. We can at least show it works. No, go ahead.
I was gonna say, can I ask a first off basic question? The title of your entire presentation was about regolith, right? Is that the plume that comes up upon the
Yeah,
roof?
the
Okay,
regolith.
that was just the first question. Second, for the fact that you're shaking the dust off of a window, is the dust still not gonna be just in front of the window? Like what is actually getting it out of your frame of view?
So the glass itself is bonded to the edge, and with that shake, we're just hoping to cause it to bounce off and get redirected away from the camera lenses. Hopefully not further, because like the lunar regolith has a lot of problems sticking to things.
Okay.
Usually that's because of its charge, so that's what the EDS shields would be for. But if it sticks to the window, it can completely block the vision. And let's say a crater opens up underneath, or something happens to the landing site itself that's unknown. The vision system that's not caked with dust will hopefully be able to detect that change and make it a quick adjustment to protect the safety of the crew. That's kind of the whole concept of it. We're just trying to keep as much of the vision clear as possible, because if you know we're not gonna be able to do every single particle.
And you talked about using it in conjunction with another system.
Yes.
Okay.
Yeah, it can't stop like abrasive nature like stuff. It can prevent it from adhering to it and blocking, but it won't stop like high velocity scratches and stuff. It'll just bounce that material off.
A lot of the
what
things
you-
we were seeing with the human lander challenge was a lot of people were going after the abrasive nature of the regolith and tackling that problem. So we were like, okay, let's try to change up the design a little bit, and let's fix like vision, because it's something that they even mentioned. I think we saw that in a couple
Yeah,
times
they
in
were
the
mentioning,
competition.
yeah,
They're like, we need more people to do
Yeah.
vision systems.
a lot
that's
of
the big
people
part.
weren't tackling that.
Yeah, the other stuff doesn't work if you can't see where you're landing on.
And we were hoping that like, hey, this design will also work because it's so flexible. We can just attach to other materials. Eventually, even stuff like the landers and like the lunar base itself, when starships come in or whatever the other Blue Origin systems are, blow that dust. Those habitats can then use the system to shake off all that dust that's generated and clean up those areas too.
We have seen some theories about using this on the actual landing gear itself, but that is much more theory and it would be much more hard to pull off because it's, outside. But that is the current method that I've seen that they're attempting to use, but I don't want to include that because that's mostly theory at this point and there hasn't been a lot of experimentation on it.
This application is relatively. I think the paper that we found was what, 2023 last year.
Like 2022. Yeah.
And that's what we're kind of like, oh, this should work, because it seems like it's a promising concept, and it seems like as long as we can apply it to different materials, it should be good. So
Yeah, last year's Aero One class was doing what again kind of regular focused technologies, and I think they were looking at mounting two landing gear. I don't think I'm not 100% sure. They might have been doing something with like piezo, like dust removal from some of the landing gear actuation systems.
one
That would be a
one
lot harder
did
to pull.
EDS. They did an electrodynamic shift system.
Yeah.
And I know because my friend was there. So that was their concept of wanting to do that. So that's what we were hoping to do another bit, and that was more geared toward abrasion and preventing clogging. This is geared mostly toward the vision systems. Some of the other designs we came up with were either already in development, like we were talking about creating a landing pad, and we found that there was an actual landing pad system already out there that ejects ceramic into the exhaust. And then we're talking about using a sub-satellite to like LiDAR the system, but all that's way too complicated for the scope of the class.
And our
I guess we
idea
went
is
too simple.
at least original for what it's trying to do. So that's what we're focused on. Any other questions? Confusions? Advice?
Overall great job. Just like you can just consider in your final presentation, probably you need more stuff. Take full advantage of the 30 minutes. Yeah.
We'll definitely add numbers, but we weren't sure as a first run through, like it's because you were showing us those slide through is like super filled with numbers. We're like, okay, we don't want to do that. We're hoping that we can just talk our way
That
out
is
of it.
another extreme.
Yes.
Right,
okay.
no numbers.
Find it nice, happy.
Yeah.
Yeah.
And if we
So-
can get the prototype, should put any
Yeah,
performances.
yeah.
Okay.
So I think I've talked to you guys several times, like the first link you asked me to buy, it leads to nowhere, unless you got to send me email
We-
to show me what you actually want to buy.
Yeah.
I still didn't receive the email. I
Oh.
cannot place the order.
Well, we can go to Lowe's and get glass. It's not that big of a deal. We can go get plexiglass or something for super cheap.
Okay.
Yeah, the materials.
The- the- Unironically, the glass is the least important part of that order.
Okay, I'll place order for the other thing, so you can actually do something.
Yes.
Yeah, we don't know how effective that's
So yeah, just consider this a test run for your final presentation.
Yeah,
So
yeah.
the thing that you need to be careful in your final presentation, and also in your report, like I make the structure analysis report and resubmission on Friday.
Yeah.
You guys have a lot of work to do.
Well, so
Yeah.
we can talk to you in class about that too, but we're
Yeah.
really trying to hammer home of our entire point of failure for our design is the voltage, and that, like,
There are a lot of things you can consider. I mean, the box itself would fail, and also when you attach something to a glass window, will cause like the original window is designed for no vibration force on it. Now you attach something and make it vibrate, will cause the structure failure of
When
it.
you take off, actually you're experiencing the most like extreme amounts of vibrations during takeoff.
Yeah.
So I'd imagine the windows would be
the
able to
oscillation
withstand
is
that.
still
Yeah.
minor. So like in terms of just a small.
Pretty much not visible.
Persuade me using some analysis. And also the whole static analysis part, either you need to think of other way to do it, otherwise the whole logic is wrong. So the whole
Yeah,
You
we
know
know
what?
that part. There's not gonna be any if there's suddenly force on the component box, there's a lot more problems going on in Starship than just our system failing.
the
So
logic behind it is wrong.
yeah,
Yeah. You consider the fastener favors and then calculate the stress of everything else. You consider the bounding electricity bound favors and calculate stress everywhere. The
Yeah,
whole logic
that's-
there is wrong. So if you want to redo that part, you need to consider like the big logic of the structure analysis.
yeah, that part we're probably just gonna take out because
Okay.
there's no reason why force
Anyway.
needs to be there.
Anyway, if you remove it, that's fine. But don't put something that's completely wrong there to think that you add more content to your report.
Yeah.
And also the thing you just said, you probably need to like show me the details.
Yeah. So the biggest thing I think we're gonna try to tackle is figuring out like more so we're gonna make sure we include all the data on the oscillations and all the frequencies and stuff like that as well.
Yeah.
Because I mean it operates within bounds, it's just we need to visually show it. We targeted this more as a marketing presentation.
Okay.
For your experimentation, are you able to find multiple thicknesses of glass?
Lows.
Okay.
Yeah, we
Well,
can.
Because I'd probably test over multiple thicknesses to make sure that the actual everything is consistent and it backs up with what you're saying, where the thickness of the glass doesn't actually matter all that much.
Our limitation right now is the PCT plates. Everything else is relatively easy to get. PCT plates, we bought the one we ordered is 1.8 by 4 and it's already in the $150 range for one, and it's like I forgot how thick it is. It's just super.
We only got one.
Yeah. Well, it's 120,
Yeah,
150
yeah,
for a
that's
super thin plate. We're like, well, I can't order anything else after that. So
We won't be able to test all. We won't be able to show the thickness of Starship with just one. We won't be able to simulate that because one will not be effective.
because even then we were planning with tempered glass being built in layers, these windows being built in layers, we're planning to put that in between the layer that faces the outmost edge and then the next layer of glass.
So that's something up, right? I mean, if you're talking about a solid pane, I haven't even looked to see if there's information about what type of glass they're using in Starship. But a piece of tempered glass, right, where you've got like multiple layers sandwiched with squishy stuff in between, right? That's going to damp out vibrations, reduce the effectiveness of your type of system, right? So if they've got like a solid pane of borosilicate, that's going to be different than something like a car windshield, right?
Yeah,
I think it's 3 layers. Three layers of glass, right?
It's
Rycor, something like that.
Yeah, because I think it's built like
98
Apollo.
silica. Yeah.
Because Apollo had the layer of they had the outmost layer, then a gap, and then a layer inside.
Yeah.
Like from in terms of like panes. Yeah. So
Well, if you've got an air gap, right, like that's a different story. You've got like a I'm thinking like a car window, and I don't know if there's any reason to design it that way, but if you've got like a sandwich structure where you've got things bonded to each other, a bonded layer of like effectively like plastic in between 2 panes of glass, right? That's going to behave and vibrate differently than like a solid piece with an air gap behind it to another solid piece, right? That's something to consider as you're trying to determine is this an effective system? And if I'm Glenn Shotwell, and deciding like, are we going to put this on our structure? Like, I'm not going to design my window to meet your needs.
No, exactly.
Right. So being able to show that you're actually going to work in a reasonable facsimile of what's being used to the extent that you have the data available to you. But the whatever you can do to estimate what reality is going to be beneficial.
So for the experiment, if we got like 3 different types of glass, bonded them together, and then showed it worked even though they're bonded together, would that be a good example?
or we can
I mean,
just-
not exact.
If that's how how you suspect the windows are built. Like
Layers
if you
different
can, if you can
glass.
say, hey, this is Apollo's approach, and we show that it works on Apollo, that's a lot better than
Okay, gotcha.
just here's a piece of glass.
Right.
It whether that is or isn't what's on Starship, at least it's like something that has some heritage in the industry and has been used, and you can show it's good there.
Yeah, it provides a good proof of concept.
Yeah.
We also saw I was seeing some new research coming out about PZT weaves, where it's like a mesh layer that could actually be sandwiched in between individual layers of like tempered glass and then run a current through the entire glass to cause the same effect. But there's no way for me to figure out how any of that is actually viable versus all that, and that would have to be designed. So
That's even newer than this.
yeah.
Yeah.
So I mean, a weave that would be built into the glass would probably be the most ideal solution. Kind of like how the ones that can turn opaque and clear, but
Yeah.
that'd be
If they do use this design and ever like at any point, it's not going to look anything like ours. It's probably going to be more seamless design like NanoWave, but we can't.
Okay, thank you. Great job.
Hey, appreciate it. Yeah, thank you for the advice.
So, do you guys want to talk to me over Zoom, or I don't plan to go to class this afternoon?
you can stay here.